Here's another example from calculus. Suppose g is the inverse function of a differentiable function, f. If f of 4 is equal to 5, and f prime of 4 is equal to 2/3, find g prime of 5. Okay, now the thing about this problem solution is to realize that g is f inverse. G is the inverse function, and they gave it to us. Simply giving to us implies that the function is invertible. So the first thing we're going to do, we're going to try to use the formula that we saw in the textbook, where we're able to find the derivative of an inverse function without explicitly finding the formula for the inverse. So let's start out, let's do this step 1. We'll call this step 1. Find g of 5. Okay, we know that g is equal to f inverse. That implies that f is invertible. We wouldn't be talking about g, which is f inverse, unless we knew that the function f was invertible. Well, if we know that f is invertible, and we know that f of 4 is equal to 5, then f of 4 being equal to 5 means f inverse of 5 is equal to 4. In other words, we just swap the x and y coordinates. And in the language given to us in the question, since we call g f inverse, then saying that f inverse is equal to 5, f inverse of 5 equals 4 is the same as saying that g of 5 is equal to 4. Okay. So the next thing we want to do, step 2, we want to show, before we use the formula from the text, show that f is 1 to 1. Well, we already know that f is invertible from step 1, so let's say it. F is invertible. That's the same as saying f inverse exists. And if we know that f inverse exists, or that f is invertible, we know that f is 1 to 1. Okay, so let's go on to step 3. We just want to make sure we meet all the qualifications to use the formula. The last qualification before we can apply the formula is to show that f prime of f inverse of 5, which is going to be our denominator in the formula, we have to show that that is not equal to 0. Okay, let's do that. We'll start by saying f prime of f inverse of 5 is equal to f prime of g of 5. And the reason this is true, I'll note it right here why it's true. It's true because g is equal to f inverse by the definition of g given in the problem. So we just replace f inverse with g. Now we say that this is equal to f prime of 4. And the reason for that, we just substituted g of 5 with 4. We just discovered that in step 1 because g of 5 is equal to 4. So that's from step 1. And then f prime of 4 is actually given to us in the information where they stated that f prime of 4 is equal to 2/3. Okay, so here we have, I'll put a little box to keep track of this. This is f prime of f inverse of 5. But the main thing that we did this for, or we should say here that this is because it's given. The main reason we did this was to demonstrate that this is not equal to 0, so let's make sure to say that. Okay, it looks like we've met all of the required conditions to use the formulas, so step 4 is apply the theorem. Okay, so what we're asked to find at the beginning was g prime of 5. G prime of 5, according to the definition of g prime, that's equal to the derivative with respect to x of f inverse of 5. Now I'm just using the definition where they told us at the very beginning, suppose g is the inverse function of f. Then g prime is a derivative of that inverse function. Now we apply the formula right here. Apply the theorem right there. That is equal, since we met all of the conditions above, that's equal to 1 over f prime of f inverse. So this is a prime first, and then an inverse function next. This is a composite function acting on 5. 1 over f prime of f inverse of 5. Well, that's equal to 1 over f prime of 4. And that's because we showed that f inverse of 5 was equal to 4. F inverse of 5 was equal to 4, which was actually shown in step 1. And that is equal to 1 over f prime of 4. Well, that's the same as 2/3. That's given information. And then if we simplify that, we just take the reciprocal of the denominator, and this becomes 3/2. And that is our final answer.